Well, hello again, my friends. Let's continue on with our making of solutions videos. So in the last one, we looked at the energetics and processes of, different types of intermolecular forces between solute and solvent and how those factors can influence the solubility of a solid, right? Or any solute in that case. So what I want to do today, we did the enthalpy diagrams and all that. Let's just take a quick look at a specific example. We'll look at, generic solution formation for ionic solution. So we take a soluble ionic solid, plop it in some water, boom, right? You're cooking your spaghetti or whatever you do. You got a pot of water, sprinkle a little salt in there, shoop, it's gone. What happens on the molecular level? Well, this does, right? You've probably seen this many, many times. I teach this in intro chemistry. But what I want to do is let's take a look at what's happening on the atomic molecular level. Then we'll do an enthalpy diagram for it and look at a theoretical way to kind of estimate the energetics involved in this process, right? The enthalpy of solution. We talked about that three-step process. Separate the solvent, separate the solute, recombine them. So you go up, up, and then down, endothermic, endothermic, exothermic, and you'll see if you end up with an overall exothermic or endothermic, or even end up at the same spot to get an ideal solution. Hey. So you could take any ionic compound here, doesn't matter. In this one I have them in a 1-to-1 ratio. I did potassium bromide. You could have picked anything, right? Sodium chloride is a typical example you're going to see. So this is the solid crystal lattice, right, before we drop it in water. Let's make the red ones the potassium ions and the brown ones the bromide ions. So bromide ions are going to be a little bit bigger than the potassium ions. Remember, cations shrink from the parent atom and ions grow. That's not going to be always the case. That the cation is smaller than the anion, depending on what the cation is and what the anion is, right? If you got fluoride, that's a little tiny anion. If you got rubidium, that's a really big cation. But potassium bromide's, fairly similar to potassium chloride. And we got that nice three-dimensional lattice going on there. Now, if we drop that in water, now these polar water molecules just are like piranha. They go blah, 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 and they're banged depending on temperature and stuff. We're going to look in the next video at the other factors that influence solubility, temperature being a big one, right? So these water molecules, so if my fist is that crystal lattice, right there. These water molecules are going to be going boing, 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 like piranha attacking something in what movie did I see? Something about Zed or some Lost City of Zed. I can't remember the exact name of the movie back in the early 1900s, something like that. These explorers going through. I forget what somewhere in Amazon. I don't know. Don't quote me on that one. But going down this river and somebody falls in the river. Gets hit by an arrow and falls in the river, and then the piranha just goes. It's like, oh, what a horrible way to go. That's unfortunately how I envision ionic solids, soluble ionic solids. You drop them in water, the water of the water molecules piranha, and they go blah, blah, blah. My mind's all messed up. It's okay. It helps with chemistry. So these water molecules, obviously one side is partially negative towards the oxygen, one side's partially positive or towards the hydrogen. Well, if they approach a cation, in this case the potassium ion, if they hit and rotate a specific way where the partial negative of the oxygen is by the positive cation, that's an attractive force, right? That's an ion dipole force of attraction. Now, one water molecule probably can't overcome the interionic forces between the cation and anion because those are stronger, right? But there's a lot of piranha in the water. You know what I mean? You get a whole bunch of water molecules, boom, they can pull that ion right out, and it sinks off into the depths, right? Like Leonardo DiCaprio sinking at the end of Titanic into the ocean water. Bye-bye, right? Spoiler. And it goes off, and then it gets surrounded by a whole bunch of different water molecules that all orient the same way, with the oxygen, the partial negative oxygen, pointing towards the potassium ion, or whatever the cation is, giving you the ion dipole forces and a whole bunch of them. That process is called hydration, and there's the energy involved with that is called the hydration energy. Right on? Well, the same thing will happen to the anion, except the water molecules will rotate so that the partial positive, where the hydrogens are, and they get enough of them and pop that, sound effects optional, right? And then you hydrate the anion, which is surrounded by water molecules with the hydrogen side facing it, the partial positive side. And it kind of forms this little sphere. You ever see those videos of people, you put on this big plastic bubble thing full of air and you run around like this, bang into people, right? So the people inside are the cations and anions, and then the sphere of water molecules around it, that hydration sphere, is that bubble part, and you see people bouncing off each other. It's pretty funny. We'll get into the equilibrium of the factors of this in a later topics, but that's essentially on a molecular level or atomic level how an ionic solid is going to dissolve, and it'll just keep going, peeling off surface layers until the entire ionic compound is dissolved, and you can see it happen, right in front of your eyes. That's what's happening. Let's look at the energetics of this and show how we can do a real quick theoretical estimate of the hydration energy involved in this process. Here's how we're going to look at this. Now, remember, this is a specific case now. We were looking at generic cases in the last video, so we're going to kind of combine things around a little bit. So here's a theoretical three-step process for taking a soluble ionic compound, solid, and then hydrating it, right? Dissolving it in water. First, remember, we got to separate those ions. Now, what's different is that we've got two different ions. We got the cation and anion, so it doesn't quite fall in that beautiful generic, scenario we did in the last video. Well, the only thing we've really talked about in that scenario is from when we talked about solids and the lattice energy. Remember, the lattice energy represents how those interionic forces between the cation and anion. It represents how much energy it takes to separate those. Technically, the lattice energy is the energy change when you bring the gas phase cation and anion together to form 1 mole of the ionic solid, which is usually a very high negative process because that's an exothermic process, very favorable. Well, this is the opposite, right? We're trying to separate them. So if you look at the solid, and then separate it into the ions in the gas phase, that is the reverse of the lattice energy. Remember, Le is lattice energy, so that'd be the negative value of the lattice energy. And if lattice energy is typically negative, and you take the negative of that, that's going to be highly endothermic, which would make sense. Trying to separate those ions from each other and break those electrostatic intermolecular forces, that's going to take a lot of energy. So that first step will be very endothermic, which follows what we did in the last video, separate the particles of the solute. Now, separating the particles of the solvent and then recombining the solute and the solvent, we're merging together in this process, in this case, called the hydration of the ions, cation and anion, which I showed you on the last board, right? The water molecules pull out the ions, surround them, get those ion dipole forces. So first, let's take that potassium ion in the gas phase and then surround it with a sphere of water molecules and hydrate it, that hydration process to get the potassium ion in the aqueous phase. Well, let's call that delta H2, the second step. That's the hydration energy of the cation, and that's typically, in every case I've seen, going to be an exothermic process that releases energy. You're forming those ion dipole forces, right? So delta H1, step 1, the reverse of the lattice energy. Delta H2, hydration of cation. You could flip 2 and 3. It doesn't matter if you do the anion or cation first. And then in step 3, we're going to do the same thing for the anions, in this case bromide. Take bromide ions in the gas phase, surround them with water, hydrate them, and you get the bromide ion in the aqueous phase. So delta H3, the third step, would be exothermic, hydration energy of the anion. You can look these values up, or they're provided for you. We could even combine this with the solids and stuff, and I could have you do a Born-Haber diagram and calculate the lattice energy and use it to calculate the enthalpy of solution, right? Forming a solution of this ionic compound. Yay, that'd be a really long problem. So if you take Hess's law and add all this together, right, you've got a potassium ion in the gas phase on both sides, so those cancel. You've got a bromide ion in the gas phase on both sides, so that cancels. So everything on the left, gone. You just have the potassium bromide solid. On the right, those are gone. You have a potassium ion in the aqueous phase, bromide ion in the aqueous phase. So here's that process of the dissolving, which we showed you in the beginning. That's what we were after on the last board. And the enthalpy of solution for this process would just be the sum of those 3 enthalpy values. Well, let's do an enthalpy diagram and calculate that. I'll give you some approximate numbers for this. Let's do it. Let's put this all together in an enthalpy diagram and estimate the enthalpy of solution for any ionic solid, as long as I give you the values. But let's do it for potassium bromide. All right, so here's our enthalpy. We start with the ionic lattice by itself and the solvent by itself. Boom! First thing we're going to do is get those cations and anions into the gas phase. That's the reverse of the lattice energy, right? That's delta H1, so that's highly endothermic. And then we're going to hydrate the cation, so that'll be the second one, and that's exothermic. So you get the K plus aqueous, and we still have the bromide in the gas phase. We haven't touched it in the water. And then we hydrate the bromide ion. So now we got K plus in the cation in the water in the aqueous phase, and the anion in the aqueous phase, forming the homogeneous solution, right? Homogeneous mixture called a solution, right? And that'll be the third enthalpy change, and that, of course, hydration energy of the anion would be negative as well, exothermic. And then we end up slightly above. Now, you could end up below, equal, above, depends where you go. But typically, you're going to end up for soluble ionic compounds very close to where you started. Most of them, I mean, probably 95% are going to be slightly in the endothermic space there. Some might be slightly exothermic, a little more on the rare side. But that difference between your starting point and your ending point is your delta H of solution, your enthalpy of solution. And if we can't do that directly, we can use Hess's law to follow that process. So that plus that plus that should equal that, right? Path 1, right? From here to here. Path 2, from here that way, kind of like a Born-Haber diagram. So the enthalpy of solution, again, will just be the sum of those three. Thank you, Hess's law. And again, delta H1 is the reverse of the lattice energy, so it'll be negative of whatever that lattice energy is. And if I provide you that, it's a piece of cake, right? Delta H2 will be the hydration energy of the cation, in this case, the potassium ion. And delta H3 will be the hydration energy of the bromide ion, right? Or whatever anion you're dealing with at the time. So I poked around, let's use lattice energy for potassium bromide of negative 671 kilojoules per mole. We could have done a Born-Haber diagram to do that. Oh, that would have been fun. So negative of that, we'll make that positive. That's why it's endothermic going up. Remember, chutes and ladders. Everything you want to know in chemistry was from board games in your childhood. That's the hydration energy of potassium. Let's use about 320 negative 300. Big difference between negative and positive. Negative 320 kilojoules per mole, because you're forming ion dipole forces. You're forming intermolecular forces. That's going to be favorable in exothermic. And let's use for delta H3 the hydration energy of the bromide ion, negative 348 kilojoules per mole. So these are probably approximate values here. Will only be good to the ones place on this. Add them together. So 671 minus 320 minus 348, you end up with positive 3 kilojoules per mole overall, a slightly endothermic enthalpy of solution. So you end up just a little bit above where you started. Well, if it's endothermic, we know potassium bromide, sodium chloride, I think sodium chloride is about 5 kilojoules per mole. We know they dissolve. We can drop it in water, you can see it disappear. But if it's endothermic, you go, how could that happen? It requires energy. Well, there's more to it. That's why we have more to go in this semester. So when we get into thermodynamics later, we're only looking at one part of all of these processes. We're only looking at the heat part of it, the enthalpy part of it. Well, there's a whole other factor we're going to get into. You've probably heard of the term entropy, right? So we're taking a highly ordered solid and forming a highly disordered solution. That's very favorable in the laws of nature, right, in entropy. So it turns out, even though this might be slightly endothermic as far as energetically, it is overcome by entropy. So we're going to find out later it's a combination of the entropy and the enthalpy in a particular way. But that's for a later time if you're still interested, all right? But we're learning. Got it? Got it good? So that's the basic idea of dissolving ionic solids, and a specific example of a Born-Haber, kind of not a Born-Haber diagram, but an enthalpy diagram for that. So what I want to look at next is we're talking qualitatively how solutions form. So what I want to look at are the factors that involve that and how much you can actually dissolve in a particular solvent called solubility. I have a visitor.